Kia ora Year 9, here's part 2 of these videos on how to convert fractions into recurring decimals. So in this one I'm going to give you a bonus skill, which is how to do long division, which is something quite old-fashioned, but it comes in really useful in strange places in maths. So the first thing we're going to do is look at what we mean by long division. Let's just find a blank page. Okay, so in the last video, so you need to have watched part 1, we did things like this. We did, for example, where's my pen? So 7 nights, we could have done like this, right? So this is called short division, because every time when I'm carrying, I can do it with just like one number here. So we get these zeros and we just have one digit up here. But when we get longer problems, we have an issue with that. So we have a different method that we call long division. So let's start with nothing to do with decimals. Suppose that I want to figure out, without a calculator, and without good numeracy strategies like many of you guys have got, so 5,472 divided by, let's do 3. So this is one that I can do by short division, right? So we go like this, we go 3's into 5,472 and off we go. So 3's go into 5 once, 2 left over, 2's go into 24 exactly 8 times. So that's good, those two are done. 3's go into 7 twice, we've got 1 left over, so then we have 4 here, right? So that's short division. Now, what if instead I had 5,472 divided by 12? So this is where long division comes in, because this divisor has got 2 digits. So we're going to write it like this. So we start the same way. So the thing that we're dividing, which is called the dividend, is 5,472. But this time, instead of just focusing on that 5, we look at the first 2 digits here. So we look at the 5, 4, and we really do think of that as 54. It's 54 hundredths. So we say 12 goes into 54 how many times? So our basic facts and our quick multiplication has to be pretty strong for harder problems like this. So 12 fours will give me 48. Let's just get rid of that underline there. That's better. So 12 fours are 48. So we subtract this. And we say 54, take away 48. Well, that leaves me with 6. Now, I'm carrying down the 7, so it's a bit like carrying in short division, only we're pulling down the next thing over, right? So we've got 12 going into 67, so 12 5s will give me 60. 67 take away 7 leaves me with 7 left over. And now I'm pulling down that 2, right? So 12s go into 72 6 times, and this was a nice one on purpose, and it's got no remainder. So that's what we call long division. Now, when we want to do harder recurring decimal problems, we often end up doing long division. So I'm not going to, in this video, have any for you to do directly in here, because I want you to get through it with these written out in your book once you've understood them, and then on to Dr. Frost to do the work that I've set you on there. So let's look now at our first one, which is how to write 7/12 as a recurring decimal. So we're going to start out the same way. We're going to have 12 going into 7. So 12 goes into 7 no whole times. We're going to put a decimal point down here, and here we're going to just write down a 0. Now we can put a decimal point there, but we usually don't, right? It kind of just visually distracts from what we're trying to do. So we're really thinking about 12 going into not 7, but 12's going into 70. So 12 goes into 70 5 times. So we can put the 5 down here. 12 5s is 60. That leaves me with 10 left over. How many times does 12 go into 10? Well, it doesn't go in one whole time, so we have to pull another 0 down from here. So we can think of these as just a series of zeros after the decimal point. 12 goes into 100 8 times. 12 8s are 96. So we subtract the 96 from the 100 and we're left with 4. 12 doesn't go into 4, so we pull down that 0. 12 goes into 40 3 times. 3 12s are 36, and we've got 4 left over. So we pull down another 0. 12 goes into 40 3 times. Seems like we might have seen this before, right? So we've got 40 again, and we can just keep going forever and ever. So we've found our recurring part, but it's a bit funkier than the earlier ones we did, because here we've got the 0.58 and the recurrence doesn't start till after that. So 7/12 can be written as 0.58333 ... which is 0.583. And we just put that recurrence dot over the recurring part, so it's just over 1 digit. Now, the next one I want to look at is a little bit more taxing on your brain, which is how I do 11/13. So I want you to pause the video and have a go at that one, and then I'm going to work through it here. Okay, so hopefully you started off like this, 11/13. So we've got 13 going into 11. So 13 doesn't go into 11, so we've got 0 point something here. So how many times does it go into 110? Well, you're going to have to do some working on the side, so probably. So 13 eighths will give you 104. So we've got 6 left over, and we carry the 0. 13 fours are going to give me 52. We bring down the 8, and carry the 0. Right, 13 wholes go into 80. How many times? So 13 fives will give me 65. We can do one better than that. 13 sixes will give me 78. So we get 78 here, and we're carrying the 2. 13's going to 20 one whole time. We've got 7 here, so 13's going to 75 times. It's pretty annoying with this going up and down, but there you go. So we've got 65 here. Now, as we're going, we want to be looking at whether we're starting to repeat. So 13's going to 53 times, so no repeats yet. 13 threes are 39. So down here, what have we got? Well, we've got 11 here, 110. Now, are we back to where we started? Yeah, just about, right? So 13's going to 110 8 times. 13 eighths, 104, and we've got 6 here. So you can see we've come back to the start of our pattern, and we've got 13 fours are 52. So we've got our recurrence out, right? But it's quite a long one. So 11/13, we'll write that out nicely. 11/13 equal 0.846153, and then we start again. All right, now what I want you to do is some practice on your own, because I know you've been watching tons of videos. If you now log into the Dr. Frost website, and you'll see a task that's called something like this. It's called 9 Ruru extension, and then it's called converting fractions to decimals. And there's no deadline on that because it's completely optional. But if you open up that worksheet and then do the examples in your book, so you really need to be doing the working thoroughly, not on the computer. The computer's just there to give you the questions and for you to pop in the answers at the end. But when I come round, I'd like to be seeing some lovely setting out like this as you go. Okay, so that's all for today. Let me know how you get on, and have fun with these. They're quite cool. Now, there's only one thing left to talk about, which I know some of you are going to ask me, is if I've got some numbers like pi, can I write pi as a recurring decimal? And the answer is no, right? There are some really special numbers that we call irrational numbers. And if you're doing Latin, you might recognize the word in here, ratio. So that means division, right? Means not. So it means that we can't write numbers like pi or √2 as fractions, no matter how big the fraction. So we could have 94726 over 11593. No matter how stupid we made those numbers, we could never get a recurring decimal for pi or for √2. And if you're interested in that, ask me and I'll point you to some really good YouTubes on those from some other people. Thanks for watching, and let me know how you go.